Okay, so let's look at an example. And this is where we really need to be careful if something is continuous or not at a particular value, is when you're dealing with your piecewise function. And so, because that's where we have multiple equations defined at different values for x. And so let's say it says for what value of b is this following function g of x, which is equal to, so the first equation is x. If x is less than -2, and let's say it's bx squared if x is greater than or equal to -2. So for what values b of this function g of x is continuous, everywhere for x. So if I just was dealing with the first equation, x, well, that's just a line, and that line is always continuous, right? If I was looking at b times x squared, b is just a coefficient, a number. So if I looked at some number times x squared, that's just a parabola. That parabola is continuous everywhere. The problem here is that it's a piecewise function. And so when we're changing our value of x, when we're changing what value of x changes the equation, we have to be careful. We need those values to give us back that same y value. So we want to figure out what value of b, if any, that we can choose to make this continuous everywhere. And so the only place that it might not be continuous would be at that jump, or changing equations at x equals -2. So let's first look at the limit as x approaches -2 on the left-hand side. So if I'm approaching -2 on the left-hand side, that means that my values of x in here are smaller than 0. Smaller than -2. And so that tells me that I have to use this equation, the first one. So this would be the limit then as x approaches -2 of the first equation, which is x. So if I go in here, direct substitution, this would just give me back -2. Now I want to look at the limit as x is approaching the right-hand side of -2 of this function g of x. And so in this case, these are values, x are bigger than -2 because I'm coming in on the right-hand side of -2. And so this would tell me that I'm using the limit x approaches -2 on the right. I'd have to use that second equation. So b times x squared. So if I go in here and I do direct substitution, I'd have b times, plugging in -2 for x, so -2 quantity squared. So this would be -2 squared is 4 times b. So this would be 4b. So for the, again, the limit to exist, these have to be the exact same value. And then I know that -2 would have to equal this 4b, or 4b would have to equal this -2. Because we know left and right-hand side have to be the same. So let's solve for b. Divide both sides by 4, we get b then has to equal -2/4, or reducing it, -1/2. One other case has to occur in order for it to be continuous. That value, f of the value that we're looking at, which is -2 in our case, has to be the same. So let's look at f of -2. Actually, it's g of -2, sorry. So let's find g of -2. So go back in and figure out which equation you're using. Well, if x is -2, this tells me that I'm using the second equation. So I have b times -2 quantity squared, or 4b. So it does exist. Let's go back in and just show if I have g of x is equal to, let's go back in and plug in b equals -1/2. So this would be x if x is less than -2. This would be -1/2 x squared if x was bigger than or equal to -2. So in this case, if I plug this in, this would be, so g of -2 is -1/2 times -2 quantity squared, -1/2 times 4, which is -2. So it exists. Notice that my left-hand side limit here, that limit was equal to -2. If I make x or b equal to -1/2, that right-hand side limit was also equal to -2, which equals g of that number. So those three conditions hold, and we showed that if b is -1/2, then this function would be continuous everywhere. So we showed the limit exists, and it equals g of -2, which equals -2 in this case. So therefore, it has to be continuous at x equals -2. And because these are both polynomial functions, it's continuous everywhere where x is less than -2 and continuous everywhere where x is greater than or equal to -2. And therefore continuous. For every value of x. Okay, so for this example, it gives us a function and it asks us at what points are the function continuous. So if we were given, let's say f of x is equal to the fourth root of 3x minus 1 underneath that radical. So find what values of x. Is f of x continuous? Okay, so we have to be careful here. We need to look at the domain of f of x. So looking at the domain, you're looking at all values you can plug in for x and get back a real number. And so because this is an even powered radical, I can't have negatives underneath the radical because that would give me back an imaginary number, not a real number. And so we need to be careful. We need to say, okay, for a domain, 3x minus 1 has to be greater than, it's possible to take the fourth root of 0. So greater than or equal to 0. So depending on what type of function this is, when we're doing an inequality, we solve them differently. Linear, we can solve just kind of like it was a equal sign. We just have to be careful if we divide or multiply by a negative number. So I could isolate, get x by itself. So add 1 to both sides. I get 3x's greater than or equal to 1. Divide through by 3. I have x has to be greater than or equal to 1/3. And so I know that 3x minus 1 is always continuous. And I know the fourth root of a function is always going to be continuous if that value underneath the radical gives me a positive number. And so we can say then that this is continuous, f of x is continuous, basically on our domain from 1/3 to infinity. Okay, so it will be helpful if you guys remember about asymptotes. So remember, you can have asymptotes when you have a rational function. So I just kind of want to recall the following. So a vertical asymptote, this occurs when you're going towards some value of x and your graph either blows up to a positive infinity or shoots down to negative infinity. And so now that we have the terminology of limits, we can write it like this. So we have a vertical asymptote occurs if we look at the limit as x approaches some value, let's say a, of some rational function, f of x over g of x, and this either equals plus or infinity or equals negative infinity. Okay, so pictorially, remember we denoted asymptotes by a dotted line. And so this is saying as we're getting closer and closer to our value of x equals a, maybe on the left-hand side of a, this could be shooting upwards. As we're approaching x equals a on the right-hand side, this also could be shooting upwards. So notice it's not ever hitting any particular y value. That y value keeps growing. And since it's not hitting any particular y value, then we have a vertical asymptote there. They could be going opposite direction. One could be shooting downwards. One could be shooting upwards. But they're either going to positive or negative infinity. Also remember that vertical asymptotes, we can never cross a vertical asymptote. So a graph never crosses a vertical asymptote. To find vertical asymptotes, let's just call it VA for short. So to find the vertical asymptote, you're looking for find values that set the denominator equals 0. But not also the numerator. If you found the value set both the numerator and denominator equal to 0, it's undefined there, but it's actually a whole. So note if a value sets both the numerator and denominator equals 0. We have a hole in the graph. So it's important to make sure that it's not setting both of them equal to 0. If it's only setting the denominator equals 0, then we have that asymptote. And then horizontal asymptotes. So kind of a review over horizontal asymptotes. So now that we know about limits, we can use limits to define this. So horizontal asymptote occurs if you're going off to positive infinity or negative infinity of your function, and it's a rational function. So let's say f of x over g of x. This goes towards one y value, L. So if we were to look at what this looks like on a graph, so again, we denoted asymptotes usually with a dotted line. So maybe this is where L is. And as your function is going off to infinity, this graph is going to get closer and closer to this line y equals L. So there's an example of what could be happening. It might come down like this. And as we're going to negative infinity, we're also heading towards the y value of L. Okay. It can cross a horizontal asymptote. So no. Graphs can cross a horizontal asymptote. If it does, it's still going to start hugging that line as we go to positive or negative infinity. So it might cross it, but then start headed, be above that line, but still getting closer and closer. And then how do we find them? Well, that really depends on what your numerator and denominator, the degree of those are. So there's 3 possibilities when finding a horizontal asymptote. So to find a horizontal asymptote, you need to find the degree of the numerator and find the degree of the denominator. Okay, so just so we don't have to write this out each time, let's say y was equal to some function f of x all over some function g of x. Let's say we looked at the degree, and the degree of f of x, let's say it is equal to n. And let's say we looked at the degree of the denominator of g of x, and we got back m. So recall degree of a polynomial, you're looking at the highest exponent, and that highest exponent, that number is what the degree is. So there's 3 different cases that could happen. The degree of the numerator is bigger than the degree of the denominator. So n is bigger than m. If that's the case, then there's no horizontal asymptote. Your numerator is growing at a faster rate than your denominator. And so since it's growing at a faster rate than the denominator, that's going to be heading off to positive or negative infinity. If the degree of the denominator, m, is bigger than the degree of the numerator, n, so the degree of the denominator is larger, that means that the denominator is blowing up faster than the numerator. And if you have a small number over something huge, that goes to 0. So there's a horizontal asymptote at the x-axis, which that equation of the line is y equals 0. And then the last case scenario that could happen if you're looking at the degrees, they also possible they're equal to each other. So maybe m is equal to n. If that's the case, there is a horizontal asymptote. And it's at y equals, let's say, a over b, where a is equal to the leading coefficient of the numerator So leading coefficient is the number in front of the variable raised to the highest power. And b is equal to the leading coefficient of the denominator. Okay, so only going to have a horizontal asymptote if it's a rational function we're looking at. And then it depends on the degree of the numerator denominator depends on if it has one or not. Okay, so let's pull out some examples. So find the limit of each as x goes to infinity, as x goes to negative infinity. You may wish to visualize your answer with a graphing calculator or computer, or just guess. Is what it says. So let's say we're given that g of x is equal to 2x cubed plus 7 all over x cubed minus x squared plus x plus 7. And we want to find the limit as x approaches infinity and the limit as x approaches negative infinity. So looking at this, I would look at my degree of my numerator and I would look at the degree of my denominator. So if I'm looking at the degree of this numerator, the highest power is 3. If I look at the degree of the denominator, so the highest exponent is also 3. And so looking at that, if they're the same, then we look at the leading coefficient of the top. So I'm going to call it LC, leading coefficient of the top Well, that number in front of the x cubed is a 2. So leading coefficient of the numerator is 2. And if I look at the leading coefficient of the denominator, so the number in front of x cubed in this case, there's no number, it's 1. It's 1. So I can tell that I have a horizontal asymptote at y equals my leading coefficient of the numerator, which is 2, divided by the leading coefficient of my denominator, which is 1. So y equals 2. So if I'm looking at the limit as x approaching infinity of g of x, I know that this value is going to give me back 2. And if I look at the limit as x approaches infinity, negative infinity of g of x, this is also going to equal 2. So if you don't like to do it that way, remembering about your rules of exponents to find horizontal asymptote, there's another way that you can kind of think about this. If you have the limit as x is approaching positive or negative infinity of 1 over x, or even 1 over x to the nth power. I'm going to say that n is bigger than or equal, or is bigger than, can't be negative, because if I have a negative exponent, that would bring me up into the numerator. And it couldn't be 0 because that would just make that 1. I guess that would still give me, so n has to be bigger than 0. If that's the case, again, if you have some number over something that is blowing up, then 1 over a huge number goes to 0. So if you want to do this and you're looking at this limit, let's go back to what we had before, of our function 2x cubed plus 7 all over x cubed minus x squared plus x plus 7. Notice if we did direct substitution, we would get this infinity, because 2 times infinity cubed plus 7. That number is going to continue growing up to infinity. If I plugged in infinity down here, all over infinity, this is an indeterminate form, just like 0 over 0 was. And that doesn't mean anything to us. So there's a trick where we multiply by this fancy 1, and our fancy 1 is going to be 1 over x raised to the nth power, where x to the n is, actually maybe we should say where n is the degree of the denominator. And we're going to make this, because this really technically isn't 1, so we'll say multiply by 1 over x to the n all over 1 over x to the nth. So a fancy 1. So notice if you do that, if I multiplied everything through by 1 over x cubed.
Hello, this is Bill from Yeah.
So it said that you unenrolled in one of your classes. Was that you or what?
I enrolled in unrolled?
Yeah, it says.
Okay. So in our case, n is equal to 3. The degree of our denominator. So if we go through here and we divide every single term by x cubed. So we would have this limit here as x goes to infinity of 2x cubed over x cubed plus 7 all over x cubed. And then divide every term in the denominator by x cubed. So we would have x cubed, let me just do it first, minus x squared plus x plus 7. So if we divide all of these terms by x cubed, before we take the limit, let's simplify this a little bit using the rules of exponents, division, same base. We subtract. So 2x cubed over x cubed just gives me 2. Nothing simplifies with 7 over x cubed. X cubed divided by x cubed, well, that's 1. Minus x squared over x cubed is 1 over x. Plus x over x cubed, that gives me 1 over x squared. Plus 7 over x cubed. So if we go in here and we plug in infinity wherever we see an x, notice those are in the denominator. So as this x goes to infinity, 7 over infinity cubed, this whole piece right in here goes to 0. So same thing in the denominator. This minus 1 over x, 1 over infinity would go to 0, 1 over infinity squared goes to 0, and 7 over infinity cubed goes to 0. So these little pieces are all going to 0, which would leave us with the 2 in the numerator and the 1 in the denominator, which is 2. So we have a horizontal asymptote at y equals 2. So either way that you think about it, you'll get the right result. So you can use what you had learned in algebra, looking at the degree of the numerator denominator to determine if there's a horizontal asymptote, or now we can use this fact that this limit as x goes to infinity or negative infinity of 1 over xn always goes towards 0. And using that to manipulate things to look like that in that rational expression, so we can tell that those pieces are going to 0 and figure out what the limit is.
And that looks like it applies both for the positive and negative variant of infinity. Is that right?
Right, exactly. So for instance, it says find the limit of each as x goes to infinity and x goes to negative infinity. So let's say we had f of x was equal to pi minus 2 over x squared. So again, it's going to find limit as x goes to positive infinity of f of x. Well, we can use our rules of limits here. Pi is just a constant. We can look at this as, the limit of our constant. Minus the limit of x goes to infinity of 2 over x squared. Well, remember, the limit of a constant is just that constant itself. So this is pi minus, well, if we're plugging in values here as x is going to infinity and squaring it, that denominator is blowing up, and this whole value is going to be shooting off to 0. And so I have pi minus 0, which is going to give me back pi. And same idea when I'm looking at the limit as I'm going to negative infinity. So if I look at b, the limit as x goes to negative infinity of f of x. Well, this is the limit as x goes to negative infinity of my first function pi, which is just a constant, minus the limit as x goes to negative infinity, the second, which is 2 over x squared. If I take negative infinity and square it, that's in the denominator, it's blowing up rapidly. Even if that was a cubic or whatever, it would be approaching 0, but it would be negative numbers getting closer and closer to 0. But it's okay because they're both, either way, they're both going towards 0. And so again, we get pi minus 0, which is pi. And if we looked at the graph of that, we would see that we would have a horizontal asymptote at pi. Pull that up real quick. Okay, so we were just pulled up decimals. We graphed the function. We were just looking at that limit as x went to positive and negative infinity. And looking at this, notice that this y value is approaching pi 3.14 as we go off to infinity. So same idea as we're going off to negative infinity, that y value we're getting closer and closer to is pi. If you look at it here, notice that we actually have a vertical asymptote at x equals 0. And recall those were values which set our denominator equals 0. And so if we go back to our function, what sets our denominator equals 0, but not also our numerator is 0. It's undefined at x equals 0.